Recall, if a Lie group K acts on a manifold M, we have a map well, let's see. I'm going to say it slightly differently. Then for any vector in the Lie algebra, we have a vector field. Let me call it x sub m, defined by, if you want to know what it does at a point, you exponentiate the vector field, act on the point, you get a curve, and take the derivative at time 0. Okay. The map, well, from the Lie algebra to the vector fields, x goes to x sub m, is, and well, here's where the signs strike again. It's a Lie algebra map, but maybe with a sign thrown in. The bracket of, I'm going to ignore this sign because usually, pretty soon we'll be looking at the abelian groups. The brackets will be 0 and I won't have to worry about it. But people go through a big song and dance about whether it's a Lie algebra map, anti-Lie algebra map. Sometimes the Lie algebra is redefined as right invariant vector fields, then it is a Lie algebra map. And this is what McDuff and Solomon do. Now, if action of K on M preserves a symplectic form, omega, then let's see what happens. For any x in the Lie algebra, the Lie derivative with respect to this induced vector field is 0. Right? Now let's see. I'm slowly going towards the definition of the moment map, which you have seen half a dozen times by now. But maybe we should have the official definition on the blackboard, just for fun. So this is D contraction. Well, and then there is another term where you take D of the 2 form and then contract, but that's 0. So let me just remind you that you get 0. So that tells you that this contraction is closed. Right? So now suppose this contraction is D of something. Right? So for example, if your cohomology vanishes and then you close one form, the appropriate cohomology vanishes and you, one form is exact. That happens on vector spaces. It happens if on simply connected manifolds, right? Then, so this is for some mu upper x smooth function, right? Then, what's the scribble? Then we'd like to say action is Hamiltonian. If you remember the first lecture, this is the definition of x sub m as the Hamiltonian vector field of mu sub x. Right? Just to remind you the notation of the notation. But usually, One requires a bit more. Right, there are Lie brackets floating around. Let's see. There is an action of K on its Lie algebra. Right, this is the adjoint representation. So we get a dual representation, or I guess contragradient is the word people use. Which is defined by this is called coadjoint action. Let's see, add dagger at some point in the group acting on a covector paired with some vector. Again, I'm using angular brackets for pairings. Vectors, these are the covectors. That's by definition the covector on add of A inverse on X. Right, and this inverse is thrown in, so this is actually a representation, a homomorphism rather than anti-homomorphism. So we require that the map mu, here is the moment map in its full glory, defined by, well, it takes the values in the dual of the Lie algebra. So if I pair it with a vector, I should get a function. So this guy is in M, this guy is in the Lie algebra. And the pairing is non-degenerate, and it's defined by mu upper x at the point x. This is a long sentence, equivariant. So maybe I'll just, right, so what does it mean to be equivariant? I want that mu of A acting on X is the coadjoint action on mu of X.
Is this automatically equivalent when K is average?
You might have to average. Right? You don't, right, this implies that mu x, mu y, not immediately, that this bracket is the bracket you have to differentiate this. Okay. And I may be messing up a sign, so let me just put this little sign here. You don't know these guys commute on the nose. There could be a constant. Right? You know that in the abelian case, this Lie bracket is 0. So this is 0. But you may not have arranged your functions so that they Poisson commute on the nose. I think you have to be just a tad careful, right? So I don't want to fuss with it, so I'm just going to require that whatever moment map I have is equivariant to begin with, since I can always arrange it. Right, so mu is called the moment map. Right, so you have seen the moment map in the first lecture, but for some reason it was taking values not in the duo over the algebra, but in Rn. But that's because we picked coordinates for the torus. And we identified the duo of Rn with Rn. We identified the algebra with torus with Rn, and identified the duo with Rn because they're standard bases. Okay, so now I assume K is a torus, is a compact connected abelian group, also known as a torus. But I wanted to think of my tori this way because I don't want to pick a basis of the integral lattice. So if action of K on M omega is Hamiltonian, and mu from M to K do the corresponding moment map, let's see what I get. Then for any x, y in the Lie algebra, if I look at the Lie bracket of the induced vector fields, that's really the Lie bracket of Hamiltonian vector fields. The notation gets out of hand here, right? So I'm taking components of my moment map. These things are called components of the moment map. By definition, this is the induced vector field. The induced vector field is Hamiltonian. Now we've computed before that this is the Hamiltonian vector field where this is the Poisson bracket. And now this is by equivariance mu of the bracket, which is the Hamiltonian vector field of 0, you get 0. So this abstract definition of the moment map is the old one we had before concretely. So flows of xn, yn commute for any x, y. Remember in the first lecture I started with n commuting Hamiltonians. Now I'm not picking them. So we get Hamiltonian torus actions. But without choosing a basis of, and with apologies to the other lecturer, Tomo, I'm going to call the integral lattice Z with K, which is the kernel of the exponential map from the Lie algebra to the group. And if you can take notes and think at the same time, you might wonder, why on earth am I writing the kernel of the exponential map? Right? The exponential map on our arbitrary Lie group is not a homomorphism. But for abelian Lie groups, the exponential map is a group homomorphism. So this is a group under addition. This is a group that we started out with. And so note exp of x plus y is xx exp y for abelian Lie groups. So it makes sense to talk about the kernel. Okay. I don't know if this was a bit too fast. Okay, so now let's go and start looking at neighborhoods of orbits. Okay, so assumption K torus action is Hamiltonian with moment map mu. So note, since for any two vectors in the Lie algebra, remember we said that they're Hamiltonians Poisson commute, right? But now what do you see? This is, if you remember all the signs, I think by our convention, it's the Hamiltonian of vector field of the first, Hamiltonian vector field of the second, but with a minus sign. I don't know why I'm being careful now when I've been completely careless through the rest of the lectures, but here we are. And this is, I'm sticking in the induced vector fields. But notice what it's telling us. It says that for any point x in M, the tangent space to the orbit is just various vector fields evaluated at that point. Right? What's the tangent space to the orbit? You pick any direction in your Lie group and you move in that direction, and that gives you all possible directions in the orbit. Right? So this equation tells you that this vector space is isotropic in the tangent space, in this symplectic vector space. Remember, isotropic means if you take two vectors, stick them into symplectic form, you get 0. Right? I'm just writing it down for emphasis. Okay. So let's see. And did we do the computation of dimensions in lecture 1? I think at this time, right? So this implies that dimension k is less than or equal to 1/2 dimension m. Right? See lecture 1. Because I can't remember what I did 1. I'm not sure if you do. Maybe it's easier for you. I just have my notes. Now let's see what it tells us about in the Toric case. We should be able to get a lot of mileage out of this. Now assume dimension k is 1/2 dimension m. Right, we're in the Toric case. So let's fix a point and look, fix a stabilizer, and look at the tubular neighborhood, and see what we can say about the slice representation. So fix x and m, h, k sub x, stabilizer x. We have a representation, rho from H to GL of the tangent space. Right? But in fact, we can also choose a compatible k-invariant complex structure. Okay. Right? So, and that tells me rho from H to GL is really unitary. So we have rho going from H into the unitary group of this space with respect to the complex structure, symplectic form, metric, I don't know. I'm not sure what the right notation is. Right? But there is this triple of invariant structures floating around. Also, this subspace is invariant, is an invariant subspace. So that tells me that J of it is invariant. And if the two are equal, then we have a complex subspace floating around. But they're actually not, right? So here's an aside. Maybe I'll do it on the other board. In fact, this guy intersecting this guy is exactly 0. And then I have orthogonal complement to both of them, which is a Hermitian vector space. So let's see. So here's an aside. I'm not sure what to call it. It's tempting to call it a Kähler vector space, but I guess Hermitian is the right word, right? Right, we have a complex structure. Omega is really the imaginary part of a Hermitian form, and G is the real part of a Hermitian form. Right, we have these three compatible structures, and any two define the third. And suppose, so remember what that means. It means omega of J. J is omega, and G of dot dot is, I forget my conventions. Is it omega with the J in the first slot? Something like that? Okay. All right, now let's see. Yeah?
Back to this unitariness.
Yeah.
Is it possible to have this rho outside of UN? Don't talk about this almost complex structure and just simple algebra equation. Is it possible to send torus into GL outside of UN?
Yeah, well, there is no UN fixed, right? I have some abstract vector space and a bunch of structures floating around. If you pick a basis, you identify it with UN.
So just if you can just pick a basis and then make it into inside of UN.
Right.
So you don't actually need an almost complex structure from outside.
Sorry? No, it just sends, it preserves, this representation preserves an almost complex structure, and it preserves the imaginary part of the Hermitian form. So it preserves everything else. So it's unitary.
So this J is actually coming from the symplectic structure now.
We build it, remember? We chose one.
But if, suppose you are not talking about symplectic structure.
Then this is not unitary in general. Right? It could be odd dimensional. Right? If your manifold is three-dimensional, there is the... Yeah.
But the tiny space is J invariant?
Yes. Right, that's what an almost complex structure does, right?
No, the tiny space of orbit.
No. Is H. And I was about to go and show you that these guys are completely different. Right, so here's an aside. Vector space U in W isotropic implies that U intersect J U is 0. They're totally real. Here's the proof. For any U1, U2, and U, if I look at G of U1, J of U2, what do I get? I claim that they're actually orthogonal to each other. Right? Because this is omega of J of U1, J of U2, which is omega of U1, U2, and that's 0. Right? That's the proof. These two spaces are orthogonal. So. Also, for any U and U, let's see, if I look at omega of U, JU, that's, this is J. Let me stick, which way do I want to do it? Right, this is bigger than 0 for any non-zero U, right? And that tells me that if I look at U, direct sum JU, this is symplectic. Right? I have, for every vector here, I can find another vector here so that the pairing is non-zero. Right? And I can split off a complement. Right? So W is U plus JU plus another bit. And it doesn't really matter which structure I use to pick the complement. I could use the metric, or I can use the symplectic form. I'll use the symplectic form. This is symplectic perpendicular. Or Hermitian perpendicular. So here they are. I have a complex subspace. Here's another complex subspace. They're all split. Is this okay? Or should I define symplectic perpendiculars? I haven't really done it. Yes, no? Going once? Going twice? All right. Okay, so what does it tell me about the representation? It tells me that this representation now, remember J in this case is invariant under the action of the isotropic group because it's an invariant complex structure. So everything goes through for representations. Right? As a representation. And if you look at this, notice what this is. Right? This is the tangent space to the orbit, and this is the complement. Right? So this is the fiber of the normal bundle. This is the slice for the action of k at x. And notice that it has a piece that's isotropic, and then there's another piece which is symplectic. So this guy is called symplectic slice. Okay. So we've split our representation. Now note we actually know what the representation is on a big chunk of it. So here's another aside. Action of h on k on the tangent space at the identity coset, it comes, right, this is the usually identified with the quotient of one Lie algebra as subalgebra, comes from the adjoint action. Adjoint, capital A. Right, it's not hard to check that what I mean by comes from adjoint action is that there is an adjoint representation of k on its Lie algebra. You can restrict it to a subalgebra, to a subgroup. That representation preserves the Lie algebra, so it acts on the quotient. Right? But the point I'm going to make is, well, let's see. So this is a typical orbit. What happens in the case of tori? There is no adjoint action. So the action of h on this guy is trivial. Okay, so this is fixed. J is equivariant. Action J is fixed as well. Not much I can do. But remember, this representation on the slice has to be faithful. Right? This is somewhere we made the assumption that our action is effective. And out of the effectiveness of the action, we get that all the slice representation is faithful. So we get that the representation of H, well, I'm calling all representation in rho, so the unitary group of V is injective. Right? This is fixed, this is fixed. The only place it could be injective is into here. Okay? Now the only thing left to do is count dimensions. Let's see. What's the dimension of V? Let's compute the real dimension. That's twice dimension. It's dimension m minus, right? Here's dimension m minus this piece, twice dimension of the orbit. Right? So this is dimension m minus twice dimension k minus dimension h. Now, if you're fast enough to do arithmetic, let's see. Dimension M is twice the dimension K. This is 0 since M is K toric. Right? So I have a unitary representation of my abelian group on some complex vector space, whose dimension is twice the dimension, and it's faithful. Have an injective map into a unitary group. Okay? So let's see what we can get out of that. Notice that these arguments use nothing. Even I can understand them. Let's see. So let H naught be connected component of 1 in H. Right? Off the top of our head, we don't know that H is connected. We have H naught mapping into UV, dimension V, real dimension V. Well, let's see, complex dimension V is dimension H naught. So let's see. I have a torus sitting inside the unitary group. Now we scratch our heads and try to remember how big a torus, the maximal torus is inside the unitary group. Well, if you pick a basis, the torus is just the diagonal matrices, and that's real dimension n, right? So, well, so rho of H naught, well, this is an abelian group, is a maximal torus. By dimension count. Well, now you remember your linear algebra. You look at all the unitary matrices that commute with the diagonal ones, and what do you find? So if I have a unitary matrix that commutes with all the diagonal matrices, no, it's again diagonal, right? So centralizer of a maximal torus, I don't know, T in UV is T, but rho of H sits in the centralizer, right? We start with an abelian group. So that tells me that rho of H equals H naught. Magic. What does it tell you about H? It's perhaps unfair of me to pause and let you guys think.
In rho of H is 0.
Yeah, it equals, rho of H equals H0. So what does it tell you about H and H0? Well, okay, I'll be careful. Thank you. Yeah. So, all stabilizers are connected. But we can actually get more mileage out of this. If you look at the maximal torus in the unitary group, right, the representation splits. It's completely reducible. It splits into direct sum of one-dimensional subspaces. And what do you know about the weights? Right? form right. Basically, if you pick coordinates, you're looking at an action of the standard torus on Cn. And so form. I'm just stretching out the lecture because I don't have much to say. I shouldn't give pop quizzes at the conference. Okay, it's not working. They form a basis of the weight lattice of H. Right? Think of the standard action of a circle on C, just rotations, right? That is the basis of the, this is the base, this is weight 1, right? If I have an action of a Tn on Cn, the weights are 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and that's a basis, right? But, oh, it's a, we haven't, so this basis is being picked for us by the representation. Okay, how much time do I have?
25 minutes.
25 minutes, oh well. Okay, I guess I should have waited longer. I think I have about 10 minutes worth of stuff that I want to say, but maybe I could just ad lib, and we'll see if anybody can catch any mistakes.
I'm sorry, what's the definition of weight?
So weight lattice, let me call it ZH, do, ZH, do. One definition is Hom over Z from the integral lattice.
That's what Tom.
Yeah, or you can think of it as Hom from H to U1. Right, and it's a free abelian group sitting inside the, right? Usually people think of it as sitting inside H2. It's a lattice. These are actually a basis. One more thing. If H is a subtorus of a torus K, then we have a short exact sequence. Right? But the unusual thing is, right, so there were examples written on the board where K was a circle, this was a circle, and this was Z mod 2. That doesn't split. But if H is connected, this splits. So I can write K as H cross some complement. So that tells us something about tubular neighborhoods of orbits. Actually, that tells us quite a bit about tubular neighborhoods of orbits, right? So that tells us that for any representation, rho H to on some vector space. What happens if I look at this bundle? I guess I want the U here. I don't know. I need some letter that I haven't used before. Let's use W. Right. So what does this quotient look like? K splits. So this is H cross H prime cross W, and we're dividing out by H. Right? And so you could just cancel these two guys. So this is H prime cross W, which is really K mod H cross W. And that tells you that the tubular neighborhood is trivial. It's a product. Tubular of an orbit is a product. Well, is as in is diffeomorphic to a neighborhood of blah blah blah. Right. Strictly speaking, I have this J sitting here, right? Yeah.
In this argument, K is not a torus.
Sorry?
So here, K is
Let's see. In which argument?
So K is a symmetric torus.
from there.
Yes.
K is any complex group or
Here, I don't need K to be a torus. Any compactly grouped.
here also no. Any compact
Wait. Sorry?
any compact group.
Any compact group here. That just. But this only works for isotropic orbits. There are other orbits. You can have other orbits. In general, if you have a Hamiltonian action of a compact Lie group, an orbit doesn't have to be isotropic. For torus actions, they are. So I'm sweeping under the rug a more general statement because I won't need it.
Also, you haven't used anything about the abelianness of K.
Here, nothing.
What about it?
Quite a bit. I used the fact that the stabilizer is abelian.
Yeah.
And then I did a dimension count, too. So I used the fact that it's toric. Right? So once you have product, right, you get this interesting decomposition. Right? So it looks like a torus, a vector space, and a vector space. Right? And this is really, there is an action of K on the whole thing. So what is the action of K? Well, it's an action of K on K mod H, just by multiplication on the left. And here there is a unitary representation. Right? The K doesn't act, but H does. H prime doesn't act here. So let me say unitary representation of H as a maximal torus of the unitary group with respect to some Hermitian structure. So now let me just tell you what happens symplectically. Right? This is a differential topology theorem. I'm saying what's the moment map, but it's a moment map is uniquely defined up to a translation, so I'm suppressing this fact. So let me just say that a version of equivariant Darboux theorem tells you symplectically a neighborhood of this orbit in M is up to equivariant symplectomorphism. Right, so how do you understand this guy? This is really the cotangent bundle. Cross W, where this one has standard symplectic structure. All cotangent bundles come with a symplectic structure. And this one is I had a slip here. This W should really be a V, right? This guy should be symplectic. Here I'm not assuming that W is this cross this. Sorry. One of these days I'll get over the jet lag.
No.
Yes.
What by J, K mod H, in that logic, is the first two symplectic? Okay.
Let's see what I got.
I thought the third one is also symplectic.
Wait, so this one is symplectic.
Yeah, the first two is the symplectic. Like,
Well,
isotropic and it's J of it.
right, so this is isotropic.
Yeah.
Right, so this guy becomes this.
Yes.
And the other one comes, this is the symplectic slice.
So
Right, so W was the product of these two guys. Right?
sorry. Yeah, sorry.
Right, so this is the neighborhood. This is the slice differential topologically. It's the sum of these two guys. This is symplectic, this is isotropic. Okay? If professors are getting confused, I'm not sure what's happening to the students. I don't want to think about it. Okay? And this is a constant symplectic structure. And it's a vector space with a non-degenerate two-form. Sorry, non-degenerate skew-symmetric bilinear form. Constant coefficient differential form. Right? So at this point, let's see. Right. Keep coming back to that question. What are the moment maps? Let's go back to the splitting. This splitting tells you that the Lie algebra K splits as H plus a complement. Right? So there is we've chosen a connection on this principal H bundle. This will come in when I start looking at the moment map here. So let's see. T star of K mod H is really K mod H. Remember, everything is abelian cross K mod H dual. Right? No action. And this is K mod H. Well, the dual of the quotient is the annihilator of the subspace. This is annihilator. and K dual. So the moment map is the simplest one possible. You take the annihilator and you put it in. It takes a point and a vector and sends it to the vector. The moment map on V is quadratic. So what is it? So V splits into direct sum of subspaces, one-dimensional, where these guys are the weights. So let me write down the formula for the moment map. Again, I might be off by the sign. So if I have a vector in V, I shouldn't have called V this thing V. I call it something else. It's eta. Right, because I have V here, maybe that letter is taken. So let's see what happens. We can calculate by choosing coordinates and identifying V with Cn, but it's probably better to just let the nature take its course. It's split into these irreducibles. And since all the weights are distinct, they form a basis, there is no question about how it splits. It's forced. Right? So it tells you that for any z, which I can write as z1 through z, whatever is this dimension, I've lost track of the dimensions, so let's call it n. Zn, mu on this vector space of z is summation zj squared alpha j. And now you see these. So this guy goes, this is the moment map from V to, let's see, what's the group that's acting? It goes into the dual of Lie algebra. Right? But notice we have the splitting. So there is a dual splitting. So there is a natural inclusion into K dual. That's complementary to that subspace floating around. Right? The total moment map is the sum plus a constant. And it's mu of x, eta, z is going to be some constant plus eta plus summation. Maybe I'll write direct, well, zj square alpha j. And now you see the unimodular, the piece of the unimodular polytope showing up. Right? These guys will span a linear subspace, and these guys will span a unimodular cone. And we're taking a product. Right? So the picture that you should see, right? So this is H annihilator, well, maybe plus some constant. And then here are the weights spanning the rest. Am I out of time yet? Oh, excellent. What can I tell you? Any questions about the rapid introduction to symplectic geometry? When preparing this lecture, I realized that if I don't want to prove something, I could just skip it. The organizers will throw rotten eggs at me later. Yeah, the notes here say, now you're on your own. Okay. What else can we see from this picture? We can probably see that right, you should be able to see the orbit space. Right, here's a wait. No? Let's see. Locally, M is, let's see, K mod H cross H annihilator cross V. So M mod K, remember, I divide as, there is no action in H naught, so that stays. This goes away, that's an orbit. And then there is an action of H and V. It looks like H naught mod cross V mod H. Right? What's my action on these weight spaces? Well, I'm taking my torus, projecting it onto a circle, and let the circle act in a one-dimensional complex vector space by rotations. So this is H naught cross R plus to the dimension of V. What's the orbital moment map, right? And V mod H to H star is an embedding, is a unimodular embedding. Here's the cone. Yeah. Right. So when I divide by K, let's see. What did I do now? Right, so when divided by K, the complement of H kills this piece, and there is H left over acting on V.
Cross H, divide by H.
So you can, so let's see. The line that's missing here is M at K is K cross H naught cross V divided by K cross H cross H. These guys cancel. There is no action here, and that's V mod H left over.
We're still under the assumption that the dimension of
Right. This is all toric. Right. I would be very surprised if I can prove this result in other cases. Right. And I guess one more thing that I'm going to say is, what can you say about fixed points? Right, so this is H equals K. Let's see what happens in this model. Where's my model? This is not there. This is not there. I'm just looking at the vector space. M looks like a representation of K on V as a maximal torus in U of V. So that tells you that fixed points are isolated. But we could have seen it in this full generality that, right, once I have this model, when could I have a fixed point in this model? Well, this guy goes away. This is the orbit space. And so I'm sort of repeating this. Maybe I'll stop here.